Hi everybody, in this video I'm going to go over APEX section 10.2.3 and this is the part 2 video. So if you haven't watched the part 1 video, I want you to take a second to pause and go back and watch that video before watching this one because it will make a lot more sense. Okay, here we go. So when we were talking about sound, we talked about Doppler effect. Remember, Doppler effect explains why if an ambulance drives past you, you hear that eeeew sound, okay? So let's just take a quick second to go over the Doppler effect. So I always like to think of the Doppler effect with a duck in a pond. So let's say our duck wants to go to the right. The ripples around the duck are going to start to bunch up in front of him when he starts moving. The ripples behind the duck start to spread out. Okay, and you've probably seen this happen before. And then we said that this means that if the duck was coming towards you, that would mean that these ripples have a higher frequency. So whatever wave you're talking about has a higher frequency. If the duck was moving away from you, it would have a lower frequency, right? Those waves are more spread out, okay? So when we talked about sound, frequency was related to pitch. So if it was coming towards you, higher frequency meant high pitch, and lower frequency means low pitch. And that's why if it's coming past you, when it's coming towards you, it's high, ee, and when it's away from you, it's low, ooh. So then it goes past you and you hear eeew, right? So that was what the Doppler effect was for sound. Doppler effect is also observed for light, and it actually has really interesting applications in astronomy. So for light, again, if something is coming towards you, it has a higher frequency than you would expect. If we go back to our electromagnetic spectrum over here, if it has a higher frequency, it's more blue. If it has a lower frequency, it's more red, okay? So if something emitting light is coming towards you, it's going to have a higher frequency and it's going to look more blue. And we say that it is blue shifted because it's not necessarily the color blue, it's just shifted towards the blue side of the electromagnetic spectrum. If something that is emitting light is moving away from you, it's going to have a lower frequency and it's going to be more red. So we say it is red shifted, okay? And again, it doesn't necessarily have to be a red colored object, it's just the frequency is shifted towards the red end of the spectrum, okay? And they use this in astronomy to determine whether a star is moving towards the Earth or away from the Earth, okay? So if the star is coming towards us, okay, you can see in this picture on the right side that the waves start bunching up, so they get a higher frequency, and so we say they are blue shifted. If your star is moving away from Earth, you can see in the picture on the left that the waves are spread out more, so they have a lower frequency and they become more red. So we say they are red shifted. So we can describe stars as blue shifted if they're coming towards us and red shifted if they're coming away from us. You can also use this to tell if different stars or galaxies are moving towards or away from each other, okay? So one really interesting result of this is that astronomers pointed their telescopes out to the sky and were measuring redshift and blueshift. And they found that if you put any two stars or galaxies, any two things in the sky, they were always moving away from each other. They were always redshifted from each other. And they called that cosmological redshift, okay? So in cosmological redshift, any two objects in the sky or in space are always moving away from each other. And that led to the theory that the universe is expanding, okay? So let's take a look at this. Why does that mean that the universe is expanding? All right, let's just imagine the universe as a balloon that you're blowing up. And we measure the distance between two spots on our balloon, two stars in the universe, okay? And then a little later, you blow up the balloon more, you measure it again, and you realize they're moving further away. And then you blow up the balloon a little bit more, and they're moving even further away. And you blow up the balloon a little bit more, and they're moving even farther away, okay? So these two objects are always moving away from each other. And that means that the balloon must be expanding. So if we shift this analogy back to space, if any two objects in the universe are always moving away from each other, that means the universe must be expanding, okay? We're not going to go super deep into cosmological theories and the universe expanding, but I want you to know what cosmological redshift is and how it's different from Doppler effect, redshift, blueshift, okay? Doppler effect is mostly used to just show how stars are moving towards or away from the Earth, whereas cosmological redshift is this evidence that the universe is expanding. Great. So now we're going to shift back to Earth over here and talk about how do we see color. We're talking about redshift and blueshift. How do we see color in our eyes? Well, what happens is the sun is releasing all of the wavelengths of light. White light is all of the wavelengths of light. And they come down from the sun and they scatter and they hit everything. And then the color of the object is the color of light reflected by that object. So if we have a red apple, the red apple absorbs all of the wavelengths of light except for red. The red is reflected and it bounces back to us and we see the red apple. If we had a green leaf, all of the wavelengths of light except for green would be absorbed and then the green would be reflected, okay? So for an apple, it would absorb all colors of light except red, and it will reflect red light, okay? So this is how we see things, and you're going to watch an Edpuzzle video about why the sky is blue based on this, okay? So from today, what we need to know is how light is applied to the Doppler effect, and we can determine if a star is moving towards us or away from us by determining if it is redshifted or blueshifted. We need to understand that cosmological redshift is evidence that the universe is expanding. And we need to understand how we see light, and that all of the colors of light are absorbed except for one, which is reflected to our eyes, and that is how we see color. All right, thank you very much.